In 2016, 4 physicists walked away from the 2 ideas everyone else in quantum computing was betting on and chose something almost nobody thought could scale. Not superconducting circuits, not trapped ions, light, ordinary photons, moving through silicon chips at the speed of, well, light. Today, that decision is starting to look less like a gamble and more like a shortcut the rest of the industry didn't see coming. To understand why this matters, you have to understand what everyone else was doing at the time and why it made this choice look so strange. When people imagine a quantum computer, they usually picture something out of a science fiction movie, a shining metallic chandelier hanging in a lab, wrapped in gold wiring, cooled to a temperature colder than deep space. That image is not an exaggeration. It is the literal physical reality of most quantum computers being built today. Companies like Google and IBM have spent the last decade perfecting superconducting circuits, tiny loops of metal that only behave like qubits when they are chilled down to a few thousandths of a degree above absolute zero. Other companies chose a different route entirely, trapping individual atoms in place using intersecting laser beams, suspending them in a vacuum so precisely calibrated that the smallest vibration can ruin the entire experiment. Both approaches work. Both have produced real, measurable breakthroughs, and both come with a brutal, unavoidable problem baked into their foundation. They are almost impossible to manufacture at any meaningful scale using the technology and infrastructure that already exists in the world. This is the problem that 4 researchers from Bristol and Imperial College London decided to solve differently. Jeremy O'Brien, Terry Rudolph, Peter Shadbolt, and Mark Thompson had spent years studying quantum photonics, the science of using individual particles of light to carry and process quantum information. Instead of inventing an entirely new kind of hardware from scratch, they asked a much simpler and in some ways much bolder question. What if a useful, large-scale quantum computer didn't need exotic new physics at all? What if it could be built using the same manufacturing infrastructure that already produces billions of computer chips every single year? What if, instead of fighting the semiconductor industry, you leveraged it? That question became the founding premise of PsiQuantum. And it is the single idea that separates the company from almost everyone else working in quantum computing today. Rather than building custom, one-off hardware in a lab, PsiQuantum designs its quantum chips to be manufactured inside an existing commercial semiconductor fabrication plant, the same kind of facility that already builds chips for phones, laptops, and data centers. Their photonic chipset, called Omega, is produced at GlobalFoundries' flagship fab in Malta, New York, a Tier 1 commercial foundry that has been making chips for the electronics industry for years. This is not a research prototype built one at a time by hand. This is a chip rolling off the same kind of production line that already builds the electronics inside the device you're using to watch this video. That distinction sounds technical, but its implications are enormous. Every other major approach to quantum computing eventually runs into the same wall, scale. You can build 10 qubits in a lab. You can even build 100 or a few hundred with heroic engineering effort. But quantum computers that can actually solve problems beyond the reach of classical machines are expected to need on the order of 1 million physical qubits, once you account for the massive overhead of quantum error correction. A single logical qubit, one that is stable and reliable enough to be useful, might require thousands of physical qubits working together just to correct for the constant, unavoidable noise and errors that plague quantum systems. Multiply that by the scale needed for real computation, and you start to see why so many experts have quietly worried that quantum computing might hit a manufacturing ceiling long before it hits a physics ceiling. PsiQuantum's answer to that problem is elegantly simple to state and staggeringly difficult to execute. Don't invent a new manufacturing process. Use the one that already exists. Silicon photonics, the technology of manipulating light on silicon chips, has actually been developed for decades, largely for the telecommunications industry, which uses light to move enormous amounts of data through fiber optic cables at incredible speed. PsiQuantum's bet was that this same infrastructure, the lasers, the waveguides, the detectors, the fabrication techniques, could be adapted to build the qubits themselves, not just to move data between them. Here is where the actual physics comes in, and it is worth slowing down for because it is genuinely elegant. In PsiQuantum's system, a single photon, one particle of light, becomes a qubit by taking one of 2 possible paths through a tiny structure called a waveguide. Essentially a microscopic channel etched into the chip that guides light the way a wire guides electricity. If the photon travels down path 1, that represents one state. If it travels down path 2, that represents the other. And because photons, like all quantum particles, can exist in a superposition of possibilities at once, a single photon can effectively be traveling down both paths simultaneously, encoding both states until it is measured. This approach is called dual-rail encoding, and it gives PsiQuantum's qubits a genuine advantage that other quantum computing platforms simply don't have. Photons do not feel heat. They are not disturbed by stray electromagnetic fields the way superconducting circuits are. They do not need to be trapped in an ultra-high vacuum the way individual atoms do. Light, by its very nature, is one of the most stable, least easily disturbed things in the physical universe, which is exactly why it makes such an appealing carrier for fragile quantum information. This is also where the phrase "classical computers can't follow" earns its keep, and it's worth being precise about what that actually means, rather than treating it as a marketing slogan. Classical computers, the kind sitting on your desk or humming away in a data center somewhere, represent information using bits, which are always either a 0 or a 1. Every calculation a classical computer performs, no matter how fast or how powerful the machine, ultimately breaks down into long sequences of these binary choices. For most problems in the world, this works beautifully. It's why classical computers can render video games, run spreadsheets, and train enormous artificial intelligence models. But there is a category of problems where this binary approach runs into an exponential wall, and it happens specifically when you try to simulate quantum systems themselves. A molecule, an atom, a chemical reaction, these are all fundamentally quantum objects, governed by the same strange rules of superposition and entanglement that photonic qubits rely on. To simulate even a modestly sized molecule with true accuracy, a classical computer has to track an enormous, exponentially growing number of possible quantum states. Add a few more atoms, and the computational cost doesn't just increase, it explodes, quickly exceeding the memory and processing power of even the largest supercomputers on the planet. This isn't a matter of needing a faster chip or a bigger data center. It is a fundamental mathematical wall, one that scales so aggressively that some of these simulations would take longer than the age of the universe to complete on classical hardware, no matter how much computing power you threw at them. A quantum computer sidesteps this problem in a way that feels almost like cheating, except that it isn't. Because a quantum computer's qubits obey the same physical laws as the quantum systems being simulated, they don't need to laboriously calculate every possible state one at a time. They can represent and evolve those states directly, the same way nature does. This was the original insight behind quantum computing itself, famously articulated by the physicist Richard Feynman back in 1982, when he pointed out that if you want to simulate nature, you'd better make your simulation quantum mechanical too, because nature itself isn't classical. For more than 40 years, that idea remained mostly theoretical, a compelling argument on paper without the hardware to back it up. What's changed now is that companies like PsiQuantum are racing to build machines that can actually put that theory into practice at a scale large enough to matter for real industries, not just laboratory demonstrations. That brings us back to the manufacturing story, because building the physics is only half the battle. The other half is building it enough times, reliably enough, to reach the scale where these advantages actually show up. And this is where PsiQuantum's decision to build on silicon photonics, rather than more exotic approaches, starts to look less like an academic preference and more like a strategic masterstroke. The company has now moved past the research and prototyping phase and into genuine high-volume manufacturing. Thousands of wafers, each containing many individual photonic quantum chips, are being produced at GlobalFoundries' commercial fab. This is not a hypothetical future capability. It is happening now on production lines that already exist, staffed by a workforce that already knows how to run them, using quality control processes that the semiconductor industry has spent half a century refining. When you're trying to build a million-qubit machine, that kind of existing infrastructure isn't a nice bonus. It might be the single deciding factor in who gets there first. The company has backed this manufacturing bet with a level of funding that is difficult to overstate. Since its founding, PsiQuantum has raised well over $2.5 billion, including a $1 billion Series E round that closed with backing from major institutional investors, valuing the company at around $7 billion. That funding isn't sitting in a bank account waiting for a breakthrough. It is actively being deployed to break ground on 2 flagship sites, one in Brisbane, Australia, and one in Chicago, Illinois, each designed from the ground up to house what the company calls a utility-scale, fault-tolerant quantum computer. A machine built not as a lab curiosity, but as genuinely useful infrastructure meant to solve real problems for real industries. The Australian project in particular illustrates just how seriously governments are now taking this bet. PsiQuantum recently broke ground on a facility at Moreton Bay Central in Queensland, backed by a joint investment of 940 million Australian dollars from the company and government partners combined. This facility is being built to house tens of thousands of silicon photonic chips, alongside a massive industrial-scale cryo plant, and it is being positioned deliberately within a developing technology precinct that will also host events for the 2032 Brisbane Olympics. That is not the kind of investment governments make on a speculative side project. That is the kind of investment made when a government has run its own due diligence and concluded that this technology is likely to matter, and matter soon. The United States has made a similarly significant bet. Earlier this year, PsiQuantum signed a letter of intent with the U.S. Department of Commerce for $100 million in proposed incentives under the CHIPS and Science Act, funding intended to accelerate domestic manufacturing of the specialized components the company needs, including a material called barium titanate, used to build high-performance optical switches, along with high-temperature single-photon detectors and advanced chip packaging techniques. GlobalFoundries, the company's manufacturing partner, publicly reaffirmed its long-running collaboration alongside this announcement, describing the partnership as combining its own capabilities in silicon photonics and advanced packaging with PsiQuantum's architecture to build what both companies are calling the scalable semiconductor foundation for next-generation quantum systems. On top of that, the Defense Advanced Research Projects Agency, better known as DARPA, has advanced PsiQuantum to the final phase of its underexplored Systems for Utility-Scale Quantum Computing program, a rigorous, multi-year evaluation process specifically designed to determine which quantum computing approaches are actually capable of reaching commercial usefulness, rather than remaining permanently stuck at the scale of laboratory demonstrations. None of this means the physics is easy, and it's worth being honest about exactly how difficult the remaining engineering challenge actually is, because the hype around quantum computing has a long history of running ahead of the reality. Photonic quantum computing, for all its advantages in stability and manufacturability, comes with one genuinely brutal drawback: photon loss. Generating a single, pure photon on demand is a probabilistic process, not a guaranteed one. Sometimes the process produces no photon at all. Sometimes it produces exactly one, which is what you want, and sometimes it produces more than one, which introduces errors into the system. On top of that generation problem, photons can be lost along the way, absorbed or scattered before they ever reach their destination on the chip. In PsiQuantum's dual-rail architecture specifically, it is entirely possible to lose more than 90% of the photons generated before they ever get a chance to contribute to a useful calculation. That means building a functioning 100-qubit system might require generating something on the order of 10,000 individual photons, just to end up with enough surviving, usable qubits to do the job. And unlike a classical beam of light, where you can simply amplify the signal if some of it gets lost along the way, a single photon can't be cloned or copied once it exists. This is a fundamental law of quantum mechanics called the no-cloning theorem, and it means that when a single photon is lost, that particular piece of quantum information is gone permanently, with no backup copy waiting in reserve. PsiQuantum's answer to this problem is architectural rather than purely physical, and it's arguably the company's second most important contribution to the field, after the silicon photonics manufacturing bet itself. In 2021, researchers at the company introduced a framework called fusion-based quantum computing, which restructures how error correction works specifically for photonic systems. Rather than relying purely on individual, perfectly preserved qubits, this approach uses entangling measurements between photons to build a more forgiving, more modular error correction scheme, one specifically designed to tolerate the kind of photon loss that is unavoidable in this architecture. It's a way of building resilience directly into the system's structure, rather than trying to eliminate every possible source of error through sheer physical precision. An approach the company argues is more realistic, given how photonic systems actually behave in the real world. It's also worth acknowledging that PsiQuantum is not the only company betting on light. Xanadu, based in Toronto, has pursued a meaningfully different photonic approach, using continuous variable encoding, where information is stored not in a photon's choice of path, but in properties of the light field itself, like its amplitude and phase, using a technique called squeezing to reduce uncertainty in one property at the cost of increasing it in another. Xanadu has already demonstrated genuine quantum computational advantage on certain narrow sampling problems. The company has been moving toward a public listing at a multi-billion-dollar valuation. Meanwhile, on the other side of the world, China Telecom recently deployed a photonic quantum computer called Tianyan, containing over 2,600 photons, built on an architecture called Zhuzhong, and remarkably, it operates at room temperature, offering services for graph analysis, drug discovery, and machine vision applications through a cloud platform. The race to build with light, in other words, is not a single company's quiet side project. It has become a genuinely global competition with serious institutional and government money flowing in from multiple directions at once, each one betting on a slightly different piece of the same underlying physics. What sets PsiQuantum apart within that competitive landscape is the specificity and scale of its ambition. The company has been explicit, almost stubbornly so, that it is not interested in building another small-scale demonstration machine designed to show off a narrow quantum advantage on some artificial benchmark problem. Its stated target is 1,000,000 physical qubits, arranged into a fault-tolerant architecture capable of genuinely useful computation by around 2027. That is an extraordinarily aggressive timeline for a machine of that scale, And the company's leadership has been candid that reaching it depends entirely on treating quantum computing as what they call a grand engineering challenge, rather than an ongoing science experiment. That framing matters more than it might sound like at first. A science experiment can afford to fail, interestingly. An engineering challenge has to actually work, reliably, at scale, or it fails to matter at all. Early signs suggest the company is moving from promise toward execution. Engineers have been working to bring the company's so-called alpha system to a fully cold operational state at a new facility in Milpitas, California, with early experiments beginning in earnest during this past year. It's important to be precise about what those first experiments actually represent. They are not yet running full quantum algorithms designed to outperform classical computers on useful problems. Instead, they are validating the underlying architecture itself, confirming that the individual components, the photon sources, the detectors, the optical switches, the cryogenic cooling systems, all function correctly when integrated together as a complete system for the first time. That distinction is worth holding on to because it separates genuine engineering progress from marketing. The company's own leadership has pointed out that smaller-scale quantum demonstrations from competitors, the kind that generate headlines about quantum supremacy on artificial, narrowly defined problems, often behave so differently from a true fault-tolerant machine that they provide relatively little useful insight into how the eventual full-scale system will actually perform once it comes online. There's another advantage tucked inside PsiQuantum's photonic approach that doesn't get discussed nearly as often as it probably should, and it has to do with how these systems are cooled. Most competing quantum computing approaches require extraordinarily complex cryogenic systems, giant chandelier-shaped refrigerators that must maintain temperatures colder than deep space across large, delicate structures. Because PsiQuantum's qubits are photons, and photons genuinely do not feel heat or interact with electromagnetic interference the way charged particles or superconducting circuits do, the company has been able to design a fundamentally different, more modular cooling architecture. Rather than needing everything crammed into a single massive refrigeration chamber, the company has developed high-density cooling cabinets, similar in physical footprint to the modular server racks already found in ordinary data centers, each one capable of cooling hundreds of individual quantum chips simultaneously. That might sound like a minor engineering convenience, but at the scale required for a million-qubit machine, it may end up being one of the most consequential design decisions in the entire architecture, because it means the cooling infrastructure can scale roughly the same way data center infrastructure already scales today, using construction and engineering knowledge the industry has already spent decades mastering. It's worth pausing on why any of this would actually matter outside of academic curiosity, because the answer connects directly back to that exponential wall classical computers keep running into. If a fault-tolerant photonic machine of this scale actually comes online, the first industries in line to benefit are the ones already drowning in problems that are fundamentally quantum in nature. Pharmaceutical companies spend years and billions of dollars trying to simulate how a candidate drug molecule will actually interact with a target protein inside the human body. And today, that simulation work is approximated, not solved, because the true quantum mechanical calculation is simply too large for classical supercomputers to handle exactly. Materials scientists face the same wall when trying to design better batteries, more efficient solar cells, or entirely new categories of superconductors, because the properties of a material ultimately come down to how electrons behave at the quantum level, and that behavior resists precise classical simulation the moment the material gets even modestly complex. Financial institutions, aerospace companies, and energy providers are all watching this space too, for reasons that are less about exotic physics and more about optimization, since many of their hardest scheduling, logistics, and risk modeling problems scale in ways that quantum approaches are, at least in theory, uniquely suited to handle. This is part of why the company has already begun forming partnerships aimed squarely at these applications, working with organizations, exploring computational fluid dynamics for aerospace design, and with cancer research institutions, exploring fault-tolerant algorithms for oncology drug discovery. None of these partnerships prove the technology works yet, but they reveal where the industry expects the value to show up first the moment it does. Zoom out far enough, and what starts to emerge is a genuinely different theory about how quantum computing will actually arrive in the world, one that stands in direct contrast to the popular narrative of a single dramatic breakthrough moment. The dominant public story about quantum computing tends to imagine a sudden, singular event, a headline-grabbing demonstration where a quantum machine solves some famous, previously impossible problem overnight, and the world wakes up the next morning having crossed into a new technological era. PsiQuantum's bet is quietly, deliberately different. It suggests that useful quantum computing will arrive the same way almost every other transformative computing technology has arrived throughout history, gradually, through unglamorous, incremental improvements in manufacturing yield, in error correction efficiency, and in supply chain reliability, until one day the machines are simply good enough, reliable enough, and available enough to start solving real problems for real industries, quietly, without a single dramatic headline attached to the exact moment it happened. That gradual infrastructure first framing might sound less exciting than a single dramatic breakthrough, but it also might be exactly why serious governments, defense agencies, and major financial institutions have been willing to place such large, concentrated bets on this particular approach, rather than spreading their money evenly across every competing quantum architecture on the market. DARPA doesn't advance a company through a rigorous, multi-year evaluation program because the marketing sounds compelling. The U.S. Department of Commerce doesn't propose $100 million in manufacturing incentives because a press release used exciting language. These are institutions built specifically to evaluate whether a technology is actually going to work at scale on realistic timelines, and their growing willingness to commit serious resources to PsiQuantum's silicon photonics approach, specifically, is itself a meaningful signal, arguably a more meaningful one than any single laboratory demonstration could ever provide, precisely because these institutions have far less patience for hype than the general public does. None of this guarantees success, and it's worth being clear-eyed about that before getting swept up in the momentum. The remaining engineering challenges are genuinely difficult in photon loss, error correction overhead, and the sheer scale required to reach 1 million functioning qubits remain formidable obstacles that no company, including PsiQuantum, has yet fully solved in practice. History is also full of ambitious technology roadmaps that slipped years behind their original timelines, and a 2027 target for a million-qubit machine is an extraordinarily aggressive one by any reasonable standard, even for a company this well-funded and this well-supported. But the underlying logic of the bet itself, choosing light over exotic new physics, choosing existing semiconductor manufacturing infrastructure over building entirely new fabrication techniques from scratch, is difficult to dismiss, precisely because it doesn't depend on inventing something the world has never seen before. It depends on scaling something the world already knows how to build, just built differently, and pointed at a fundamentally different kind of problem than the one it was originally designed to solve. And that, ultimately, is what makes this story worth paying attention to, far beyond the usual quantum computing headlines about supremacy claims and laboratory curiosities that fade from the news cycle within a week. This isn't a story about a single exotic machine locked away in a research facility, guarded like a museum piece and wheeled out occasionally for a carefully staged demonstration. It's a story about turning quantum computing into an industrial product, manufactured the same way the rest of the modern electronics industry already manufactures everything else, at the kind of scale that could eventually make it as unremarkable and as essential as any other chip already humming away quietly inside the infrastructure of the modern world. 4 physicists looked at the 2 dominant paths everyone else in the field was racing down and chose a third path instead, one built on light, on existing factories, and on a bet that the fastest way to the future wasn't to invent something entirely new, but to build smarter with something the world had already spent decades perfecting. Classical computers were never designed to keep up with the quantum systems this approach is aiming to simulate. And if the manufacturing bet pays off on anything close to the timeline the company has laid out, the rest of the computing world may not have much choice but to catch up.